Welcome to the deep dive. Ever find yourself looking at two different sets of numbers and trying to figure out how they stack up against each other?
Oh, definitely.
Yeah.
Happens all the time, right?
Yeah. Whether it's, comparing different workout routines or trying to understand shifts in public opinion, that ability to analyze and compare data as well, it's like a superpower.
It absolutely is. And while we often jump to spreadsheets, maybe calculations, one of the, I think, quickest and most intuitive ways to really grasp these comparisons is through visuals.
Hmm.
So today, we're diving into a whole collection of examples, statistical ones, that really showcase these different graphical methods for comparing data distributions.
Exactly. So our mission today really is to equip you with the tools to understand these visual comparisons. We're going to explore things like dot plots, double bar charts,
Back-to-back stem plots.
right, parallel box plots, and also cumulative frequency plots.
Yeah, the whole range.
By the time we're done, hopefully, you'll have a much clearer sense of how to interpret these images and, what key insights you can pull out when you're looking at multiple data sets side by side.
Sounds good.
Okay, let's unpack this then, starting with something pretty straightforward. Dot plots.
Okay, dot plots. They offer a really direct way to compare two sets of data, especially when they're measured using the same scale.
How do they work exactly?
Well, each data point just gets represented by a dot, and it's positioned above a number line. So this lets you immediately see where the data tends to cluster and how spread out it is for each group you're comparing.
Okay. And our first example 3.1, it looks at daily caloric intake for people on two different weight loss programs, right? Program A and Program B.
That's the one.
We've got the raw numbers in our sources, sure, but the dot plots, they really bring that comparison to life. You can see the distribution of calorie intake for each program sort of stacked vertically.
And what's really cool here is how quickly you can get a sense of the overall pattern. See how both distributions look, well, roughly bell-shaped.
Yeah, I see that.
That kind of suggests that for both programs, most people had calorie intakes around some central value, with fewer people way out at the extremes.
But you can also spot something else pretty quickly.
Oh, yeah. What's that?
Well, Program A seems to have a data point way out at 1900 calories, like an outlier that Program B just doesn't have.
Ah, good catch. Yes, that single dot way off to the right for Program A definitely stands out.
So when we're comparing these kinds of distributions, it's useful to have a framework, right? People often talk about SOCS, shape, outliers, center, spread.
Right, or sometimes CUSS center, unusual values, shape, and spread.
Yeah.
Basically the same idea, just a slightly different order. It gives you a checklist, so you cover the key comparison points.
Okay, so using that SOCS framework then, the shape here is that roughly bell-shaped curve we mentioned for both. And the outliers, well, that 1900 calorie intake in Program A is a perfect example of an unusual value or an outlier.
Exactly. Now let's think about the center. Even without calculating anything yet, just visually, does one seem higher than the other?
Looking at it. The main cluster of dots for Program B does seem shifted a bit to the right compared to A, maybe suggesting higher calories overall.
Precisely. The source notes visual centers around 1300 for A and 1400 for B. And if you actually calculate the averages, the means, it confirms that. 1336 for A, 1424 for B, so B is higher.
Okay. And the last letter, S, for spread. How much of the data varies? Looking at the plots, they seem fairly similar in range, except for that outlier.
Yeah, Program A goes from 1,000 up to that 1,900 outlier. Program B goes from 1,000 to 1,800. So very similar, especially if you mentally discount that one high value in A for a moment.
And the standard deviations, the source gives those too.
It does. Both are 218.
So they're identical. That really reinforces what we see visually, doesn't it? That the sort of typical variation around the center is pretty much the same for both programs?
It does. So even with a simple dot plot, you get a pretty good picture. Similar shape, similar spread generally, but Program B tends to have a higher center, and Program A has that one distinct high outlier.
Got it. Okay, let's move on then. What about double bar charts? You mentioned those. They sound like they're for a different kind of data.
They are. Double bar charts are excellent when you're comparing categorical data across two or more distinct groups.
Categorical, so like types of things, not measured numbers.
Exactly. Instead of just one bar representing categories count or percentage, you get pairs of bars side by side. One bar for each group you're comparing within that category. Makes it super easy to visually compare the groups.
Okay, and example 3.2 in our sources uses this. It looks at the percentage of young adults who recognize various photographs.
Right. Now, technically, in this specific example, it's showing recognition across different photos for one group, so it's maybe more like a grouped bar chart than a true double bar chart comparing two distinct populations. But the principle of comparing bar height side by side is the same.
Ah, okay, so each set of bars, or in this case single bars, represents a different photograph. Joe Stalin, Joe Camel, Senator Simpson.
Exactly. And the height of the bar just shows the percentage who recognize that photo. And what's striking here as you look across them are the huge differences in recognition.
Yeah, definitely. Like the bar for Joe Camel is incredibly tall, 95%, the source says. But then Senator Simpson is tiny, just 5%.
It really jumps out at you.
It really highlights what sticks in the cultural consciousness, doesn't it? This source mentions this visual caused some concern for educators.
And you can see why when a cartoon mascot for cigarettes is recognized way more than a political figure.
Yeah.
Well, it's a pretty powerful visual statement about maybe where young adults' familiarity lies or perhaps what gets more media exposure.
Absolutely. Okay, powerful stuff even with simple bars. Next up, back-to-back stem plots. Now that sounds intriguing. How do they work?
Back-to-back stem plots are, they're a clever way to compare the distribution of a quantitative variable. So measured numbers, again, for two different groups, side by side. They use a common central stem, which is usually the leading digit or digits of the data values. And then the trailing digits for each data point, they extend outwards in opposite directions from that stem. One direction for group 1, the other direction for group 2.
Gotcha. And example 3.3 uses this to look at survival years for cancer patients on two different chemotherapy drugs, drug A and drug B.
That's right. You have the list of survival times and then this plot. It really does look like two regular stem plots just mirrored against each other, sharing that central stem.
Yeah.
So the central column is the tens digit of the survival years. To the right, you see the ones digits for patients on drug A, usually arranged in increasing order as you move away from the stem.
Okay.
And then to the left, you see the ones digits for drug B, also ordered outwards. This layout lets you directly compare how the survival times are spread out for the two drugs.
So what jumps out from this visual, the source points out something interesting. While drug A had the patient with the absolute longest survival, 39 years.
Right, way out there.
And drug B had the shortest, just 1 year.
Also an extreme.
The majority of patients on drug B actually survived longer. How does the plot show that?
You can see it in the density of the leaves. Look where most of the leaves are clustered for each drug. For drug B, the leaves tend to be thicker, more numerous, around the higher stem values like in the 20s and 30s stem rows, compared to drug A, which has more leaves clustered a bit lower down, say in the teens.
Ah, I see that now. That's fascinating. The extremes don't tell the whole story about the center of the distribution.
Exactly. It's a key observation. And if we go back to our SOCS or CUSS framework, shape, well, both are somewhat bell-shaped, maybe a bit skewed, but they also have those outliers we mentioned, 39 for A, 1 for B.
Right. And center, say.
Visually, the middle of the drug B distribution definitely looks higher up the stem than drug A's. And the calculated averages confirm it again. 16.48 years for drug A versus 22.73 years for drug B. So on average, drug B patients survived noticeably longer.
Okay. And spread. How varied were the survival times?
Well, visually, drug A's leaves seem to stretch out more, right? From 3 all the way to 39, drug B goes from 1 to 35.
So a slightly wider range for A if you include the extremes.
Yes, and the standard deviations support this feeling of more variability in A. It's 9.25 for drug A, but only 6.97 for drug B.
Meaning the survival times for drug A were more spread out, more all over the place, compared to drug B, where they were a bit more tightly clustered around that higher average.
You got it. It's a great example of how this kind of visual can highlight not just the center, but also the variability and overall shape, which might be harder to spot just looking at lists of numbers.
Makes sense. Okay, let's talk about parallel box plots next. I feel like I've seen these used quite a bit for comparisons.
Yes, parallel box plots are sometimes called side-by-side box plots. They're incredibly useful. They give you a really concise visual summary of the key statistics for one or more distributions, making those direct comparisons very easy.
So what key statistics do they show?
For each data set, you get a box. This box is drawn from the first quartile, or Q1, that's the 25th percentile, up to the third quartile, Q3, the 75th percentile. So that box itself represents the middle 50% of your data, the spread of the central chunk.
Got it. The middle half.
Right. Then there's a line inside the box that marks the median, the exact midpoint of the data, the 50th percentile. And then you typically have whiskers extending out from the box, usually to the minimum and maximum values, unless there are outliers.
Ah, so they handle outliers too.
Yes, often points that fall beyond a certain distance from the box, typically 1.5 times the box width. The interquartile range are plotted as individual points, as outliers.
Yeah.
And the whisker then only extends to the furthest point within that boundary.
Okay. That's quite a bit of information packed into one visual. Example 3.4 uses these to compare prices, right?
Yeah.
Mail order labs versus 1-hour mini labs for film developing.
Exactly. We have the summary stats listed: mean, standard deviation, min, max, median, quartiles. But the parallel box plots give you that immediate visual comparison of the price distributions.
So looking at them side by side, what's the first thing you notice?
Well, probably that the entire box for the mail order labs is positioned lower on the price scale than the box for the 1-hour mini labs.
Meaning mail order is generally cheaper.
Generally cheaper, exactly. The median price is lower, and that whole middle 50% range is lower.
But else?
You can also see that the box for mail order labs looks wider, doesn't it?
Yeah, it does. And the whiskers seem to stretch out further, too.
Right. That tells you there's a greater spread, more variability in the mail order prices compared to the 1-hour mini labs, which seem to have prices clustered more tightly together.
So that wider spread for mail order, is that good or bad for a customer?
Well, that's a good question. It depends, right? It might be good if you hunt around and find one of the really cheap ones near the bottom whisker.
True.
But that wider spread also means less predictability. You might pay something closer to the top of their range. The 1-hour mini labs with that tighter box and shorter whiskers offer more consistent pricing, even if it's generally a bit higher.
Okay. And the source also mentions something about skewness, that the mean is greater than the median for both.
Yes, that suggests both distributions are slightly skewed towards the higher prices. You can sometimes get a visual hint of skewness in a box plot if the median line isn't perfectly centered within the box, or if one whisker is much longer than the other.
Interesting.
And example 3.5 just quickly builds on this, showing parallel box plots for a stock's daily price fluctuations over 5 consecutive years.
Ah, so using them to track changes over time.
Exactly. You can line them up year by year and see trends. Like maybe the median price, the line in the box, is generally increasing. Maybe the variability, the box width or whisker length, is changing. It's a really effective way to visualize how a whole distribution evolves.
So if we went back to those weight loss programs from the start, parallel box plots could give us a quick snapshot comparing the typical calorie range, the median, and the consistency for program A versus program B, right?
Absolutely. You'd see that median difference clearly. You'd see the similar interquartile range, box width, reflecting those similar standard deviations, and you'd probably see that 1900 value plotted as an outlier for program A.
Cool. Okay, one more type. Cumulative frequency plots. These sound a bit different. How do they help compare things?
They do offer a different perspective. Cumulative frequency plots compare distributions by showing the running total, the cumulative proportion or percentage of data points that fall below a certain value.
Okay, running total.
Yeah. So the vertical axis is the cumulative frequency, often shown as a percentage from 0% to 100%. The horizontal axis represents the data values themselves.
And you plot these for different groups on the same graph.
Right. By plotting the cumulative frequency curves for 2 or more groups on the same axis, you could directly compare things like medians, quartiles, and just the overall shape of the accumulation.
So think of it like, as you move along the data values on the bottom axis, the line goes up, showing the total percentage of data you've accounted for up to that point.
Exactly. It always goes up or stays flat, eventually reaching 100%.
Okay. Our example 3.6 uses this to compare the age distribution of the U.S. population in 1860 versus 1980. The plot shows two sort of S-shaped curves.
Correct. Now, how would you find the median age for each year using this plot? Remember, the median is the 50th percentile.
Okay, so I'd find the 50% mark on the vertical axis, trace a horizontal line across until I hit each curve,
Yep.
and then drop a vertical line down to the horizontal axis to read the age.
Perfect. That's exactly how you do it. And the source tells us if you do that, in 1860, the median age was around 20.
Wow, young!
Yeah. And in 1980, it was around 32.
Quite a bit older. So the plot immediately shows the population had a higher median age in 1980.
Clearly. Now, what about comparing the spread? We often use the interquartile range, the IQR, for spread. How could we find that here? Remember, IQR is Q3 minus Q1.
Okay, so Q1 is 25%, Q3 75%. I'd do the same thing. Find 25% on the vertical, go across, drop down to get the Q1 age for each curve, then do it again for 75% to get the Q3 age. And the IQR would be the difference between those two ages I read off the bottom axis for each curve.
Got it. So the source did this calculation. For 1860, Q1 was around age 9, Q3 around age 35. The difference, the IQR, is 26 years.
Okay.
For 1980, Q1 was around 16, and Q3 was way up around 50. So the IQR is 34 years.
Ah, so the IQR is larger for 1980, meaning the middle 50% of the population's ages were more spread out in 1980 compared to 1860.
That's what it shows, yes. Greater variability in the central part of the age distribution in 1980.
So these cumulative plots are really good for easily visualizing and comparing percentiles, like the median or quartiles, across different groups.
They are very useful for that specifically. And, as our source emphasizes in its summary, it doesn't really matter which of these graphical methods you end up using. Dot plots, double bars, back-to-back stem plots, parallel box plots, cumulative frequency plots.
Right.
The really crucial thing, the key takeaway, is to always consider those characteristics. The shape, any outliers or unusual values, the center and the spread. Always think SOCS or CUSS.
And interpret what those features mean in the context of the actual data.
Exactly. It's not just about making a pretty picture. It's about understanding the story that visual is telling you about the real-world situation.
Absolutely. Okay, so to kind of bring our deep dive to a close here, we've really walked through a whole toolkit of visual methods for comparing data distributions. We saw how dot plots can highlight individual points and shape, double bar charts compare categories, back-to-back stem plots give detailed side-by-side comparisons, parallel box plots offer that concise summary of key stats.
And cumulative frequency plots help understand percentiles and accumulation. Quite a range.
It really is.
And I think the big message really is to remember to look beyond just the simple average or mean. The shape of the data, how spread out it is. These often reveal a much richer, more nuanced picture when you're comparing different groups or situations.
Yeah, the average doesn't tell the whole story.
Not at all. Ultimately, these visual tools, they empower you, the viewer, to move beyond just simple summaries and really engage with the underlying patterns and the subtleties within the data. And that leads to richer, more informed conclusions.
Well said. So here's maybe a final thought for you listening. Think back to a time you encountered two sets of information being compared. Maybe it was in a news report or a presentation at work or even just a casual chat. How might visualizing that data, using one of the methods we've talked about today, have given you a clearer picture or maybe even a different understanding of that comparison?
That's a great question to ponder.
It really underscores the power of seeing your data, not just reading about it or hearing about it. Well, thanks for taking this deep dive with us.